Good morning, students. Uh, Yesterday, in my video, I have discussed the classification of the solids based on the nature and based on the binding force present between the constituent particles. Based on its nature, we classified the solids as crystalline and amorphous, and based on binding force or the attractive force present between the constituent particles, the solids are classified into four types. There is ionic solid, covalent solid, molecular solids, and metallic solids. Okay. Now, students, let me begin. After this, let me go with a word crystal lattice. Crystal lattice or space lattice. Now, since the crystalline solids, they are orderly arranged. There is a arrangement of the constituent particles is a long range arrangement. So first try to understand what do you mean by the crystal lattice. Then we go for the arrangement of the particles in different types of solids. Okay. So the crystal lattice means it is in a three-dimensional array or arrangement of the points in a space where each point represent a constituent particle. For example, if I write the points like this, these are the points where each point represent a constituent particle. It is an orderly arrangement of the points in a space in a three-dimensional manner. So that is called a crystal lattice or a space lattice. And since here, let me define another one point, that is the unit cell. Unit cell is in a smallest portion of that crystal lattice. It is selected in such a way that when it is placed side by side, above and the below, so it generates a complete crystal lattice. And another one, it is the lattice point. Let me define first these three basic terms. Here, the lattice points means it is the point which represent or which shows a relative position of the constituent particles. So this is the crystal lattice where each point indicates a lattice points showing a position of the ion or a atom or a molecule in that crystal lattice. That is called the lattice points. And unit cell, it is the smallest three-dimensional repeating unit of that crystal lattice. For example, this is the complete crystal lattice. If I join like this, so let me move some points. So this is a crystal lattice. So here, let me take this is the smallest portion of this crystal lattice. Okay, so here this is the smallest portion of this crystal lattice which represents the complete crystal lattice. So that is called an unit cell. Okay. So next one is let me go in detail about these different types of unit cells. Now, since the unit cell, once again, we classify this unit cell mainly into two types. One is the primitive unit cell, and another one is the centered unit cell. Since here, the classification of this unit cell, it is mainly based on the position of the constituent particle in that unit cell. They are mainly classified into two types. One is the primitive unit cell, another one is the centered unit cell. Okay. In centered unit cell, it is again classified into three types. One is the simple centered cell or simple cubic cell, centered cell. Second one is the body center cell. Third one is the face centered cell. And there is another one type of the centered unit cell that is observed in other than cubic systems. So that is the end centered unit cell. So this is the classification of unit cells. So this classification, it is purely based on the position of the particles in that unit cell, position of the constituent particles in that unit cell. Let me show you how the particles are arranged in different unit cells. First, let me go with a primitive unit cell. Since here in a primitive unit cell, it is also called as a simple unit cell. Simple unit cell. So here in simple unit cell, so in which the particles are present at the corners of that cube. So this is the smallest portion of that unit cell. So here the constituent particles are present at the corners. Then that unit cell is called a simple unit cell. And the second one is the centered unit cell. In centered unit cell, as I told, there are three types. So one is the body centered cell. So in body centered cell, there are 8 corner particles are present, and one particle is present at the center of that unit cell or center of that cube. So these are the 8 particles which are present at the corners, and one is present at the center of the cube or center of that unit. And the second type of centered unit cell is the face centered. In face centered unit cell, again there are 8 corner particles. 8 corner particles are chosen, and one particle is present at the center of each face. So here there are 6 faces in a cube. Therefore, there are 6 face-centered particles are present in a face-centered unit cell. And next, another one is the end-centered unit cell. In end-centered unit cell, there are 8 corner particles, and a pair of particle is present at the opposite of 2 faces. Okay, so there is the arrangement of the constituent particles in different types of unit cells. Okay, so let me again repeat that the types of unit cells. So unit cell is the smallest repeating unit of that crystal lattice, that is called as a unit cell. Unit cells are mainly classified, or unit cells are of 2 types. One is the primitive unit cell and another one is the centered unit cell. And in primitive unit cell, it is also called a simple unit cell, where the constituent particles are present at the corners of that cube or the corners of that unit cell. And in centered unit cell, there are three types. There is the body centered, face centered, and end centers. So here in centered unit cell, this has that corner particles. So one particle is present at the center of cube, means that is called as a body center. And in face centered unit cell, there are 8 corner particles and one particle is present at the center of each face. And another one type of the centered unit cell is the end centered unit cell, where the 8 corner particles are present and a pair of particle is present at the opposite of these faces. Now, so these particles, I'm saying these points represent the position of the constituent particles. So these are called the lattice points. Therefore, the lattice point, in short I am writing LP, the lattice points in simple cubic unit cell is 8, because there are 8 corner particles are present. And the lattice point in body centered cubic cell is 9, 8 corner particles and 1 at the center of the cube. So lattice points here is 9. And in face centered unit cell, there are 8 corner particles and 6 face centered particles. Therefore, the lattice points of face centered unit cell is 14. So this is about the types of the unit cells. So next students, after this types of unit cells, I written something on the board, so I'll come to that later. So before that, let me go with the parameters of unit cells. Since the unit cell, it is the smallest repeating unit of that crystal lattice. So this is the cube is an unit cell. So here, these edges, I define the edges as a height as an A, breadth B, and length as C. So A, B, C. So these are the edges of that cube, and the axial angle between this A and B, here A, this is B, and this is the C. The angle between these A and B is alpha, B and C as beta, and C and A as in a gamma. As you can see here, the edge lengths A, B, and C, and axial angle is alpha, beta, and gamma. These are called the unit cell parameters. Edge length A, B, C. This is the A, B, and C. These are the edge lengths of this cube. And axial angle, the angle between A and B, is defined as alpha, B and C, beta, C and A is in a gamma. So these axial angles and the edge lengths are the unit cell parameters. And since based on these unit cell parameters, one of the scientists called Bravius, he constructed 7 crystal systems having 14 different types of unit cells. And those 14 different types of unit cells are called as a Bravius lattice. Let me go with the different types of the crystal systems. Okay, so these crystal systems, for example, the first one is the cubic, second is tetragonal, orthorhombic, rhombohedral, hexagonal, monoclinic, and triclinic. So these are the 7 crystal systems. And the cubic crystal system has 3 types of unit cells. It is a simple cubic, body centered cubic, and face centered cubic. We discussed the simple cell means, or simple cubic cell means, the particles are present at the corners of that cube. And in body centered cubic cell, there are 8 corner particles are present and 1 at the center. Okay. Like that, cubic has 3 types of unit cells, that is simple, BCC, and FCC. We are not observed the end centered cell in cubic system. Right? And the unit cells parameters like edge lengths are same. That is the A, B, and C. Okay, the edge lengths are equal, and also the axial angle is alpha. It is also same as beta. Beta is also same as gamma, and these values are equals to 90 degrees. The example for this is the copper, aluminum, nickel. These are the few examples for a cubic system. And similarly, the other crystal systems are tetragonal, orthorhombic, rhombohedral, hexagonal, monoclinic, and triclinic. These systems we will now study in second year. We will discuss only about the cubic systems. Then also, we go through these crystal systems. That is a tetragonal. Tetragonal has only two types of unit cells, SCC and BCC. And in orthorhombic is one of the crystal system which has all types of the unit cells. That is simple, BCC, FCC, and EC. And here edge lengths they are not equal, but axial angles are equal to 90 degree. The best example is the barium sulfate. And rhombohedral, it has only one type of unit cell, that is the simple cubic unit cell. And hexagonal is also a simple cubic unit cell. Monoclinic has two types of unit cells, that is simple cubic and edge center. And triclinic has only one type of unit cell, simple cubic cell. And since here, among these 7 crystal systems, most symmetrical system is the cubic, because its edge lengths are same and also axial angles they are same and they are equal to 90 degree. And most unsymmetrical crystal system is in a triclinic. So where the edge lengths are not equal and also the axial angles they are not equal and they are not equal to 90 degree. Okay. In CET they may ask which one is the most unsymmetrical crystal system. There is a triclinic, and the one is the most symmetric crystal system is in a cubic. Okay. And the crystal system which has all types of the unit cells, that is an orthorhombic. Okay. Like that, you can practice for CET questions. In theory, they may not ask the questions regarding this. Okay, in CET it is an important. Okay. Now, students, let me go with the next one, the cubic systems. For a syllabus, we learn only the cubic system. Okay. Okay, students, the next concept in solid state is the calculation of number of particles in unit cell. Just as I told that we have only the cubic system. So in cubic system, we have 3 types of unit cells. One is the simple cubic cell, body-centered cubic cell, and face-centered cubic cell. In simple cubic cell, we know there are 8 corner particles. Therefore, the lattice point in simple cubic cell is 8. Whereas in body-centered, there are 8 corner particles and 1 particle is present at the center. Therefore, the lattice points are 9. And in face-centered, the lattice points are 14 because 6 face-centered and 8 corner particles. Now, the lattice points and the total number of particles present in that unit cell, they are different. The lattice point in simple cubic unit cell is, let me write the simple cubic. Now we are calling that as a simple cubic unit cell, or simply SCC unit cell, where SCC refers to simple cubic. So here we are having 8 corner particles. Eight corner particles means the lattice points are 8, but the total number of particles present in this simple cubic cell itself is equals to 1. Total number of particles is equals to 1. Okay. Let me show you how to calculate the number of particles in unit cell. In simple cubic unit cell, for that I have drawn here one diagram, so which contains 8 unit cells. Okay, let me show you the unit cells. This is the first one. This is the one unit cell. Behind this there is another one. So besides to this there is a one. So behind that another one. There are 4 unit cells above and there are 4 unit cells below, which are in touch with that particular unit cell. Now, if I consider the particle which is present here. See, this particle is a corner particle. It is shared by the 8 unit cells. This particle, some portion of this particle is also present in first unit cell, and some portion of this particle is also present on behind this side and behind other unit cells also. That means this particle is present in all the 8 unit cells. Some portion of the particle is present in each unit cell. Okay, so that particle is shared by 8 unit cells. Therefore, we say that the contribution of this corner particle to that particular one unit cell is 1/8. Okay. So, if I write this is the cube. So here, this is the corner particles. So these corner particles contribution to that particular unit cell is 1/8. Similarly, this corner particle is also contributed only 1/8 part of that to a particular unit cell. This also contribute 1/8. This also contribute 1/8. Right. All the 8 corner particles, they contribute 1/8 part of that to particular unit cell. Therefore, we calculate the number of particles as, let me write, therefore, the number of particles in SC is equals to the total number of particles are 8. So these are the corner particles plus into the contribution of each corner particle is 1/8. So this is the 1/8 is the contribution. Okay. Therefore, if we simplify, it is 8 into 1/8, that is equals to 1. That means the total number of particles present in simple cubic cell is equals to 1. Now, similarly, let me calculate the total number of particles present in BCC. Body center or body centered cubic cell. As says here, in body centered cubic cell there are 8 corner particles and one particle is present exactly at the center of that cube. 8 corner particles along with that plus 1 at body center. The lattice points are 8. Lattice points means shows the relative position of the constituent particles. So there are 9 particles positions are showing in BCC, but the contribution of corner particle is 1/8 and the contribution of body center particle is completely to that unit cell only. Okay, so here we write the total number of particles in this BCC is calculated as number of particles in BCC. I should call this as a body centered cubic. In BCC, there are 8 corner particles into the contribution of each corner particle is 1/8 is the contribution, plus along with that corner particles there is the one body center particle. One is body center and the contribution of this body center particle is completely to that. Okay. So therefore we consider this as a complete one particle. If I simplify this is 8 into 1/8 plus 1. So that is equals to 1 plus 1 is is equals to 2. So 2 is the total number of particles present in BCC. Okay. See, don't confuse with the lattice points and the number of particles. Number of particles are different and the lattice points are different. And next friends, the another one type of cubic unit cell is the face-centered cubic unit cell. We call that as an FCC. Instance, in face-centered cubic cell, there are 8 corner particles and 6 face-centered particles are present. 8 corner particles plus 6 face-centered particles. Corner particle contribution we know to that particular unit cell is 1 by 8, whereas the face-centered particle contribution to that particular unit cell is 1 by 2. Okay, for example, let me show with this cube. This is the one cube here. So we know there are 8 corner particles, and let me take one face-centered particle. This is the face-centered particle. So besides this, there is another one cube. Let me draw. Says okay. So this face-centered particle is shared by the 2 unit cells. That means the contribution of this face-centered particle, that particular unit cell, is 1 by 2. Like that, there are 6 face-centered particles which are present on each face of that cube. So therefore, the contribution of each face-centered particle is 1 by 2. Now, we can calculate the total number of particles in face-centered cubic cell as this is 8 corner particles is multiplied with the contribution of the corner particles is 1 by 8. This is the contribution of corner particle to that particular unit cell, plus 6 face-centered particles. 6, these are the face-centered, into the contribution of each face-centered particle is 1 by 2. 1 by 2 contribution. Now simplify this is 8 into 1 by 8 plus 6 into 1 by 2. So 8 into 1 by 8 is 1 plus 6 into 1 by 2 is 3. So that is equals to 4. Therefore, the total number of particles in the FCC unit cell is 4. Okay. So this is the calculation of face-centered particles in unit cell. Now students, let me go in let me write, this is the contribution of particles in simple BCC and FCC. Just now we calculated the number of particles and also lattice point and the contribution of each particle to that particular unit cell. Let me draw a simple table which shows lattice points as well as the number of particles in SCC, BCC and FCC. Simple cubic unit cell, the lattice points are 8. In body center, the lattice points are 9. Face center, the lattice points are 14. And the number of particles, in simple cubic unit cell is 1, because only 8 corner particles and contribution is 1 by 8 of corner particles, and BCC 2 and FCC then F4. So this is very important. Don't confuse about that lattice points and the number of particles. Lattice point shows only relative position of the constituent particle in that unit cell, and these are the total number of particles present in that particular unit cell. And since after this, there is another one important concept, that is the packing efficiency or the close packing arrangement of the constituent particles in a unit cells. Okay, so we calculate packing efficiency in simple cubic unit cell, the packing efficiency in body centered cubic unit cell, and face centered cubic unit cell. As the exam point of view, is a very important, is a fixed question in your exam. So let me continue that in our next class.